Suppose we have a partial differential equation, pu equals f. So p is a differential operator. U is some distribution. This is the unknown function that we're solving for, and f is a function that is known. Suppose we have a differential equation like this then, and we know that there exists a u. Suppose we already have existence. We're interested in the regularity of u now. So what that means is we want to find if u has any singularities, existence, we want to know where they exist and where they are. So this is what we're interested in, and in this context, I'm going to be giving 3 results involving the regularity of solutions of PDE, and actually it's going to be a bit more general than just solutions of PDE, because I'm going to be discussing pseudodifferential operators. So in the results I'll be giving, you can consider P not only a differential operator, but you can consider it a general pseudodifferential operator, or a standard pseudodifferential operator. And I'll define what that means in a second, but it's just, I guess, a more general partial differential equation. Okay, so the 3 results that I'm going to be giving are, so the first one concerns regularizing operators. And a regularizing operator is just an operator, let's say an operator that takes the space of distributions. So these are the distributions of compact support that I'm writing here, to the space of smooth functions, right? So it takes something that could have many singularities and smooths it out to something that has no singularities. So this is what a regularizing operator does. And the result that I'm going to be giving characterizes these regularizing operators. So I can give an explicit form to any of these regularizing operators. Number 2 is a result on pseudolocality. So the result I'm going to be showing is that every pseudodifferential operator, so this is going to be shorthand for pseudodifferential operator, is pseudolocal. Every pseudodifferential operator is pseudolocal. And what pseudolocality means, and again I'm going to define this in a second, it means that if I have an operator P, which is my operator that's pseudolocal, and it's applied on some U, which is the distribution of compact support, it could have many singularities, then it's going to give me an F, which is a distribution that does not have more singularities than U. So P only makes the situation of U better, right? It only makes it more regular. So this is what it means to be a pseudolocal. So P only improves F, or only improves U. And the third result that I'm going to be giving is sort of a refined pseudolocality. And so it's going to be, so I haven't defined pseudolocality, but so this will make sense in a second, but it's going to be pseudolocality swapping the singular support for the wavefront set. And so the wavefront set I won't be defining here. I've defined it in many previous videos, but it's essentially it's a more refined notion of the singular support. It tells you not only where the singularities are, but in what direction they occur. So this is going to be, so refined pseudolocality is going to be, so I guess I'd say microlocal pseudo. So to state this result, we're going to need to get into these things called microsupports of pseudodifferential operators, which is the analogous of wavefront sets for distributions to pseudodifferential operators. Okay, so this is what I'm going to talk about today, these 3 things. And so before I get into number 1, let's actually go back a little and motivate the introduction, very quickly motivate the introduction of pseudodifferential operators. So suppose I have a constant coefficient, linear PDE, or linear partial differential operator, excuse me. So we've written this many times before. So alpha is a multi-index, and PD is our linear constant coefficient differential operators. These are the constant coefficients. And so we would like to solve the PDE given by PDU equals F, right? We can assume here that F is a distribution of compact support over omega, which is our domain, and that U, the distribution we're solving for, is just an ordinary distribution. So we know from any course on the theory of distributions that if we have a fundamental solution to P, then we have solved this equation, because PD, so the fundamental solution is just a distribution E such that P of E equals the Dirac delta. So this is a fundamental solution. And if we know E, then we've solved the equation, because PD of E convolution with F is simply F. So E convolution with F is our solution. And this is in fact well defined, because F is a distribution of compact support. So we can define the convolution. Okay. In fact, this also works. So this also gives us, well, in this case, we obtained solvability of this equation because F had compact support. So we could define the convolution. But we can also get local solvability if we had an F that was, let's say, in D, right? So if F was just an ordinary distribution, then what we could do is say, all right, we want solvability of this equation in some neighborhood V of omega. So in the open neighborhood V in omega, we could have said, all right, take a test function, take phi in C infinity C, right, omega, such that phi is 1, on, say, a neighborhood of V. Okay, or we could say a neighborhood of maybe the closure of V. And okay, so we have a smooth function, so kind of like this, right, where this is V here, and this is phi, equals 1 on a neighborhood of V, and then we could just multiply this. We could multiply F by this cutoff function. Right, so we could do something like this, and then say this here is our local solution to the PDE with respect to V, because this, if we restrict this to V and restrict this to V, this is equal to F, right? Which is what we wanted. And this convolution now makes sense because phi times F is a distribution of compact support. Okay, so the existence of a fundamental solution gives us a local solvability. But this isn't the only reason. So this is one of the reasons, a very important reason why we care about finding fundamental solutions. But there's another reason, which is that fundamentals, if the fundamental solution, if E is smooth outside the origin, then PD is hypoelliptic. So to be hypoelliptic is essentially the converse of pseudolocality. Like I said earlier, it's so if you have PD U equals F, it basically says that if F is smooth, then U will also be smooth. So PD doesn't transfer regularity. It's not that PD transfers regularity that way, it transfers regularity backwards. So if we have smooth initial conditions, then we'll have a smooth solution. That's why it's interesting to have a hypoelliptic PD. Okay, so this is another reason why we care about finding fundamental solutions, right? If there's C infinity outside of the origin, then our P is automatically hypoelliptic. We also know this from our standard course on distributions. Okay, so we know that it's important to find fundamental solutions, but so how do we go about actually finding them in practice? So one idea we could have is that, okay, we have an operator PD, right? And this, we want to find an E such that this holds. So, well, an idea we might have is to, and now we're going to start doing operations without necessarily caring whether they make sense or not, whether they're well-defined, because we're just going for, we want to obtain a guess at the end as to what the fundamental solution might be. So we start with this equation, and let's just take the Fourier transform of both sides. So if we take the Fourier transform, so this hat will be my notation for the Fourier transform. Take the Fourier transform of both sides, and this PD, because of the property of the Fourier transform that it turns derivatives into polynomials, we get the symbol of PD, and this is going to be times the Fourier transform of the fundamental solution equals 1, right, which is the Fourier transform of the Dirac delta. And now we can just divide both sides by the polynomial, again, assuming this actually makes sense, and take the inverse Fourier transform. And so we end up with this guess, this ansatz, that the fundamental solution is the multiplicative inverse of the symbol of P composed with the inverse Fourier transform. And so this doesn't necessarily always make sense, because P can have roots, right? P can have roots, so this denominator can be 0, and that can be a problem. Or even if the denominator, for example, gets arbitrarily close to 0, it could blow up in a way that the inverse Fourier transform doesn't exist. So we could have a few problems here. So from this point onward, we need to assume some things, right? So this whether this exists is going to depend on the form of P. It actually, if P has constant coefficients, there's a big theorem, the Lagrange price theorem, that says this will always exist. But for the purposes of this motivation, we need to restrict what P we're looking at. So let's assume that P is the nicest that we can possibly make it. Let's assume that P is elliptic. So let's work under this assumption. And if P is elliptic, that means, by definition, that the principal symbol of P only, let's see this, it's only 0. Well, I guess only, let's see, only vanishes at the origin, right? So this means that the principal symbol only vanishes at the origin, and we can prove based on this and also the fact that that this is a polynomial, and just facts about polynomials, that the total symbol, this implies that the total symbol only vanishes in a ball of radius r, for some radius r containing the origin. Okay, and actually furthermore, we know that we can obtain that the total symbol is actually bounded below by some constant times xi to the m outside of this ball. Okay, so what we can do is exploit this and say, all right, so we don't want zeros in this denominator, right? So we can take a cutoff function, chi. Let's define chi. Define chi, let's say in C infinity C, such that chi is 1 on a neighborhood of the closure of this ball. So phi is 1 on a neighborhood of this ball. And note that 1 minus chi is 0 on a neighborhood of the closure of this ball. So if we now suppose that E, instead of being the inverse Fourier transform of this fraction that doesn't necessarily make sense, let's suppose, or I guess define E equals 1 minus chi divided by p, right? So now we have, actually we need to define this by parts, right? Because on inside BR, we still have a division by 0 here. So let's just say that inside BR, this is equal to 0. And then outside of BR, this is equal to this. And in practice, what this does is we have removed the points which are potentially problematic, which are all the points inside this ball of radius r, which is where the polynomial can be equal to 0. So you just said, you know, this entire part over here is equal to 0. And since the Fourier transform of 0, anyway. So this is 0 inside the ball of radius r. And okay, so let's just see what happens when we plug this e into our PDE. So we have what was our PDE? We had PED. Let's just write this in green now. So PED of E, and so E is this now. And so this is equal to what? So let's just keep a question mark here. We'll keep a question mark, and we'll take the Fourier transform of both sides. So let's take the Fourier transform here, and if we take the Fourier transform on the other side, we will remove this from here, and this will become P of psi. Right, and this will cancel with this. And now we take the inverse Fourier transform, right? So then question mark is equal to the inverse Fourier transform of 1 minus chi, which is by linearity of the inverse Fourier transform, we have the inverse Fourier transform of 1 minus the inverse Fourier transform of chi. And so this is the question mark. So in the end, we have PD of E equals delta minus this. But remember, this chi was in C infinity C. So by the Paley-Wiener theorem, we have that this is smooth. So the E that we explicitly calculated is not necessarily a fundamental solution, but it is pretty close in the sense that, P of E is delta minus some term that is smooth. So by finding an E of this kind, an E that satisfies this equation here for some smooth remainder on this side, does not guarantee local solvability like we had for the fundamental solution. What it does guarantee is that if E is C infinity outside the origin, then we still do have hypolepticity of P. We still do have hypolepticity of P. So this E we can call a parametrics. So E is a parametrics of P, and it's useful for studying the regularity of the solutions. Use it to study regularity. Of solutions. And so this is the motivation for pseudodifferential operators. So we've assumed that P was elliptic, right? We assumed P was elliptic, and then based on this, we've found this ball where we can cut it out with a cutoff function and define, based on this, a parametrics, right? That we can use to study the regularity of solutions to this PDE. And it would be useful to know that there exists a space where these parametrices always live, right? Because nothing guarantees so E is a parametric. We can also call the convolution with E a parametrics as well, right? So nothing guarantees that this is going to be a differential operator. Right? This might fall outside of the space of differential operators, particularly if we take P of xd, right? If we start considering differential operators of variable coefficients, then this starts to become a problem. So we would like to find a space where, given an elliptic differential operator of possibly variable coefficients, where a parametric always exists and lives in that space. This space is in fact the space of standard pseudodifferential operators. And so I'll define that space now. So definition, pseudodifferential operators. So let's say given an operator A that maps C infinity C omega. So I'll stop writing this omega in a second. We'll just assume the domain is always omega. So test functions to distributions is called a pseudodifferential operator of order m, or of order less than or equal to m, if AU of x is by definition, so U is a test function. This is the inverse Fourier transform of this A, which I'll say what this A is in a second, times the Fourier transform of U. So where A of xi is a smooth function. It is a smooth function such that for every compact set in omega, and for every multi-indices, for each multi-indices here, right, so positive multi-indices, there exists a constant big C that depends on alpha, beta, and k, such that we have this bound here on the derivatives of A. So this holds for all x and k, and for all for all xi in Rn. So what this is saying intuitively is that A behaves like a polynomial, right? So this is this kind of operator is trying to generalize differential operators, and it's doing this. This generalization is happening in the Fourier domain, right, in the frequency domain, and this A would be analogous to the symbol of our differential operator, which is always a polynomial. And so we're generalizing this A from a polynomial to something a bit more, and this bit more is given by a smooth function that satisfies this bound here. And notice that this bound is, so polynomials do satisfy this bound, and it's essentially saying that A behaves asymptotically like a polynomial, and its derivatives do in a certain sense, right? It's saying that if you take a derivative, then on this right side we can say less and less about its decay as you take derivatives, right? So I think it's actually it's better to say we know more and more about its decay as we take derivatives, right? Because we start off with a fixed index m on this side, and then as we take derivatives, we start subtracting this from this m. So then the decay of this guy actually becomes better, as is the case with polynomials, right? So we have let's say like a cubic, and then we take the derivative, we get, I guess, slightly better decay with the quadratic, and then we get even better decay, and then we get the best decay of all, which ends up being just a constant function 0. So that's what this is saying, and so yeah, this is a pseudo-differential operator. Now we have some terminology. So a pseudo-differential operator, so A of this type lives in, oh yeah, I guess I should comment also that I wrote x here, so AU of x, though A of u is a distribution, right? So what does that mean, A of u of x? Well, so this x is kind of symbolic. It's an abusive notation. Whether this is a function or not will depend on it will depend on what u is. So later we'll say that we can actually extend this operator to an operator on distributions of compact support. And then in fact this can be a distribution, so this x makes no sense. But for when u is a test function, this is actually always a smooth function. So this x does make sense, but we'll get to that in a second. So some terminology or some notation. An operator A of this kind is said to be a pseudodifferential operator of order m, and this psi of m is the space of pseudodifferential operators of order m. If we take the union of all these spaces, that is just psi. If we take the intersection of all these spaces over m real, then that gives us psi of minus infinity. And the spaces where the corresponding symbols live are just given in notation by replacing the psi with s. So this is s, m, this would be s, and this would be s of minus infinity. These are the spaces of this corresponding symbols a, right? Okay. And okay, so let's say also given a symbol little a, so given a, we say op a is the corresponding pseudodifferential operator. Okay, so op a. Okay, so we have a slightly alternate way to define pseudodifferential operators. In the end, we'll see that they're equivalent in a sense. And I'll give this alternate way now. So it's this alternate way is, instead of being based on symbols, it'll be based on amplitudes, which are symbols that depend on just an extra parameter. So we can also define the alternate definition of pseudodifferential operators. We say that pseudodifferential operator, or I guess so an operator of this type over here, right, from the test functions to the distributions, is a pseudodifferential operator if a u of x is equal to 2 pi to the minus n double integral of e to the I psi x e to the I psi, or e to the minus I psi y, multiplied by the symbol times u of y dy d psi. Right, so this is just, we've essentially written the same thing as up here, except we've expanded the definition of the Fourier transform and the inverse Fourier transform. And we've obtained this, right? So now notice that our symbols are called amplitudes because they have this extra parameter y. And the bound is essentially the same, right? The bound that defines A is essentially this one, except we have an extra derivative here. We have d gamma y here. And the c will now depend on gamma as well. And yeah, that's it. This thing remains unchanged. So yeah, we have a similar bound. And what else? Oh yeah, so the symbol spaces, were now called amplitude spaces, will now be denoted like this. We'll have 2 copies of omega here instead of 1. Same with s and s of minus infinity. And so these spaces will actually have a topology, right? We'll define the topology on the symbol space, and they'll transfer over to the topology on the space of pseudodifferential operators. We can actually define somewhat of a correspondence between symbols and pseudodifferential operators. It's not exactly one-to-one, but it's classes of symbols define pseudodifferential operators, and then using that we can transfer the topology over. So I won't get into details on that though, but I will define the topology on Sm. So topology so this will just be the Frechet space topology. induced by the family of seminorms P of K alpha beta gamma, right? Where, so these are all seminorms, and we'll be varying over alpha, beta, gamma, and the compact sets K. Or here we can just take, if we're worried about this family being countable or not, we can just take a, what's it called, a countable, there was a word for this, finite, we can exhaust omega using compact sets, right? We can just take a countable number of compact sets, right, that increase and whose union equals omega. So this is a countable family, and where each p of k alpha beta gamma of a symbol A is defined by the infimum of the constants, right, alpha beta gamma k, the infimum of the constants in the estimate that actually work. So you take the least constant that works, and that will be the definition of your P. Okay. This is topology. What else? Right. So this is all I had to say about the definition of pseudodifferential operators. Just, I guess I should give a proposition. We'll prove this later. And it's that pseudodifferential operators, they do preserve some nice properties of differential operators. So we would really expect that they would be linear and continuous, right? We would hope, and in fact they are. So pseudodifferential operators are linear and continuous. Linear and continuous from C infinity C to D, but also from C infinity C to C infinity, right? And from E to D, distributions of compact support to just the distributions. And this will follow from a regularity property of pseudodifferential operators that we'll see in a second. And another nice property of pseudodifferential operators is that they're pseudolocal. Or pseudolocal, and we'll prove this also. Which again, we said that this means that pseudodifferential operators just don't introduce new singularities into the distribution that they're applied on. They're pseudolocal, so are differential operators. Unfortunately, pseudodifferential operators are not local. Right, they're not local because they're defined with an integral. So being local just means that the support of Pu is contained in the support of U. Right, so that would mean that P doesn't increase the support of U. This is not true necessarily with pseudodifferential operators. In fact, this property characterizes the differential operators inside the pseudodifferential operators. But we do have pseudolocality. So next we'll define. Next we will define. Okay, so now I've said all I have to say about pseudodifferential operators, and now I want to talk about a different kind of operator, or a different way to represent operators, at least, that is given by a certain theorem called the Schwarz-Kernels theorem. So Schwarz-Kernels. And so this theorem says that every continuous linear map, let's say to every continuous linear map, it's called K. Unfortunately, I'm using the same letter as compact sets. So K from the test functions to distributions. So same thing that we had going on earlier. For every one of these, there exists a unique k of xy. So another poor choice of notation, I guess. So this k is an operator, and this k of xy is a distribution on omega times omega, such that, so continuous linear map, to every continuous linear map, there exists a distribution like this, such that for every u test function, we have that k of u is equal to the integral of kxy of uy dy. So if you look at this for a second, you might notice that this makes no sense at all, because well, I'm integrating over a distribution times a test function, whatever that means. But this is just physicist notation, right? As Treves says, I'm following Treves, by the way. I should have mentioned that at the beginning of the video. As Treves says, this is physicist notation for the duality brackets in distributions. So what this actually means, right? What this means is that ku as a distribution, right, applied on some test function phi, where phi, the domain of phi varies over x, or I guess the variation is represented by this variable x. This equals, by definition, right? So by definition, this equals k of xy. So now this is a distribution on omega times omega of phi x tensor product with uy. So that's what that means. And so based on this definition, so this is just continuous linear maps from the test functions to distributions. I've just represented it differently. Here I'm representing it as this duality bracket, or I guess in physicist notation as an integral, a weighted integral against this distribution k of xy. And up here, I'm representing the operator as this, right? Again, an integral, but now it's in oscillatory integral, right? I have these oscillating terms here, weighted against a symbol or an amplitude a. So here I'm weighting against a symbol, and here I'm weighing against a Schwarz kernel. Okay, so two different ways to represent these operators. Why represent it as Schwarz kernels? Well, because using this representation, I can now define some notions of regularity of these kinds of continuous linear operators. So the first notion of regularity is, I can say that k, or the Schwarz kernel k of xy, so either one works, is separately regular if it is smooth in each variable. And so what that means is, if I have something like this, and I freeze this test function here, then this will give me a distribution just in omega, and I want that distribution in omega to be, in fact, a smooth function. And same if I freeze this side here. So separately regular if it's smooth in each variable. K of xy is said to be very regular if it is separately regular, and if it is C infinity outside of the diagonal of omega times omega, right? So C infinity outside of the diagonal. And lastly, k of xy is regularizing. If it is just smooth everywhere. Right, so three different notions of regularity in increasing order of strength. And for this top one, I actually have an equivalence. So I say K is separately regular if K and the transpose of K, I'm denoting the transpose by this T to the left-hand side of the superscript, where K and the transpose are, they take tests. In fact, I won't even be using this here, so I won't mention it. So the only equivalence that I'll need is that separately regular is the same thing as saying that K, the operator K, takes the test function to smooth functions continuously and linearly, and it can be extended as a function that takes the distributions of compact support to the distributions continuously and linearly. So we have this equivalence, right? And for the regularizing case, we also have a similar equivalence, which is that K can be extended as a function from the distributions of compact support to the smooth functions, right? So this is the definition of a regularizing map that I gave at the beginning of the video. Okay, so now we have everything we need in terms of preliminaries to start talking about those three results that I wanted to get into on the regularity of pseudodifferential operators. So just put a little divide here. And I can start talking about regularizing operators. So let's start talking about regularizing operators. So these are the operators that I mentioned at the start of the video, and we can define them like this, right? Or we can define them like this. And the theorem that I want to prove is that we can characterize these guys using pseudodifferential operators. So a continuous linear operator continuous linear operator from the test functions to the distributions is regularizing. It's regularizing if and only if A is the operator defined by the symbol little a, where little a is an amplitude in S of minus infinity. So I've just characterized all regularizing operators using a specific class of pseudodifferential operators. Right? We can explicitly give the form of the regularizing operators. So to prove this, I'll prove. So let's do the proof. To prove this, let's do this side first, right? So we'll assume that A is regularizing in this sense here. Assume that A is regularizing in this sense, in the Schwartz kernel sense. So assume A is regularizing. Then there will exist a Schwartz kernel A of xy such that we would have A of u equals the integral, again abusing notation, equals this integral. Right, so we'd have this. And so okay. So if A is regularizing, we have this, where, oh no, sorry, so if A is we just get this from A being a continuous linear operator from C infinity C to D, right? We haven't yet used that A is regularizing. So A is regularizing implies that A of xy is a smooth function. Okay, so we have that it's a smooth function and that A maps distributions of compact support to the smooth functions. So what we have to do now is use all this information to obtain a symbol or an amplitude little a such that the pseudo-differential operator induced by this amplitude is equal to big A. And the amplitude that we'll choose is A of x, y, xi is equal to e to the minus I xi x minus y, A of xy, chi of xi. And this chi I will choose in C infinity C, such that the integral, its integral is equal to 1. Okay, and now let's just let's see what op of A looks like. So op of A, so the pseudo-differential operator defined by A of ux looks like this double integral of, so is this correct? We have the double integral. This might be this up to multiplication by a constant, right? Yeah, up to multiplication by a constant. We would have that this is equal to e to the I xi x minus y, e to the minus I xi x minus y. These two terms are going to cancel each other out, times a to the xy chi xi right. So we have this. This is just the definition of the operator defined by A. So we've canceled both of these guys out, and we have this remaining. Now we can pull this this chi outside of the integral, since outside of the dy integral, since there's no y in this expression. So this actually turns into the integral of xi d, the integral of chi d xi times the integral of a xy uy. And this we've assumed to be equal to 1, so this also goes away. And we're left with this, which is exactly what we wanted, right? This is exactly A of ux. And the only thing that's left to prove is that A is a symbol of order minus infinity. And to prove this, all you have to do is just write the definition, right? I guess I can write d alpha xi d beta x d gamma y e to the minus I xi x minus y. And we have to see if this is less than or equal to that part on the right hand side. And what will guarantee that it is that this is C infinity C, right? So this will be 0 outside of this will be 0 for xi big enough. So if xi is big enough, then this is 0. And since that right hand side only really has xi in the expression, we only care about the decay with respect to xi, then this in fact satisfies the decay that we want, right? So so we finished, right, with at least this direction. So the other direction is assuming, so the other direction in green, the other direction is assuming that we have a pseudo-differential operator of order minus infinity, and we must show that it's regularizing. So to prove this direction, I'll actually use a very powerful lemma. So this is not trivial at all. This lemma generalizes the fact that differential operators decrease the regularity of the space that they act on. So if I'm acting on, let's say, if a differential operator of order m is acting on some space ck of continuous functions, then it'll map ck to ck minus m. And same thing with Sobolev space. If I'm mapping, if the differential operator is acting on hs, then it will map to hs minus m, where m is the order of the operator. So this is the same thing for pseudo-differential operators. So this lemma says that if we have a pseudo-differential operator, then we can extend it we can extend it continuously and linearly, right? Continuously and linearly to the Sobolev space HSC, right? So this is Sobolev space HS of distributions with compact support. It's HS minus M locally, right? So locally Sobolev space HS minus M. Oh, sorry, actually. Yeah, no, this is right. Okay, so we can extend every pseudodifferential operator to this for every S real. And so since I'm stating this lemma, we can also state a corollary, which is that every pseudodifferential operator is separately regular. Remember we had that equivalence with separately regular. So to be separately regular means that your Schwarz kernel is smooth in every variable, but this is equivalent to saying that your operator maps test functions to smooth functions and distributions of compact support to distributions. And in fact it does, because if we have, so we know that your pseudodifferential operator for M maps HSC to HS minus M locally. So if we take the intersection of all these spaces, if we intersect over all real S's, so S, this is equal to C infinity C, and this is equal to C infinity. So at least we do maintain that the map does go from we have that the map goes from C infinity C to C infinity, and we have that it does so linearly. So this intersection gives us all the properties that we can deduce set theoretically, but the topological properties we might have to work a little bit more to obtain, right? If we want the map to be continuous, then we need to say something about it. Maybe that this has some kind of continuous embedding into all of these Sobolev spaces. I guess we use just results from Sobolev space theory, which I won't get into, but the fact is that we can just take the intersection of these Sobolev spaces and then use some short topological argument to conclude that that we have this map from C infinity C to C infinity. Okay, and if we take the union of these Sobolev spaces, we have something similar going on. Which is that this left-hand side is equal to the distributions of compact support, and this right-hand side is equal to the distributions of finite order, which is contained inside the distributions. Right, so we have what we wanted, which is that every pseudodifferential operator is separately regular. Now, going back to what we wanted to prove, so returning, we had, so assume A is a pseudodifferential operator of order minus infinity, and we want to show that it is regularizing. So the lemma says that A maps the compact support Sobolev spaces HS to the locally Sobolev spaces HS minus M. Right. Now from here we do something similar to what we did above, which is that we can take, we know that this side, for this side we can take any M we want, so let's just take M arbitrarily large, and if we take M arbitrarily large, what we have here is essentially minus infinity. This is just the intersection of all Sobolev spaces for all S, right? So if we take M arbitrarily large, that's the same thing as putting this intersecting over all S. And what that gives us on the right-hand side is C infinity. Now on the left-hand side, we can just take the union over S, and what we'll have is the distributions of compact support. Again, we would take the union over S on the right-hand side, but there is no S, so we're left with this. And again, to show, so this shows all the properties that follow from set theory, but to show continuity, we might need to work a little bit more. So we're done. So we are done with proving this theorem, or at least somewhat proving the theorem, which is that we can characterize the regularizing operators, which is they're a very important class of operators. And so now we can move on to the second part, which is showing that pseudodifferential operators are pseudolocal. Pseudodifferential operators are pseudolocal. And so to show this, I will need a lemma. I will need a lemma that says if a Schwartz kernel K is very regular, this implies that K is pseudolocal. Implies that K is pseudolocal. Okay, so now finally define what pseudolocal is, since we actually need to use it rigorously. So pseudolocality just means that the singular support of Ku is contained in the singular support of U. This is for every U distribution of compact support. So this is what pseudolocality means. Right, saying that K does not increase the singular support of U, right? It could only make U more regular than it is. So very regular Schwartz kernel implies that K is pseudolocal. So let's do that. Okay, so proofs of facts like this usually end up being proofs of the contrapositive. So we can flip this inclusion and take the complement of these sets. So this is the regular set of U and regular set of Ku. So if we can show that given that U is smooth in some neighborhood of a point x0, then Ku is smooth in some neighborhood of a point x0, then we're done. Okay, so let's define these neighborhoods. So let's define the neighborhoods U and V, open neighborhoods of omega, such that the closure V is a compact set in U. Now define, I'll write it down here, define phi in C infinity C of omega, such that phi is 1 on a neighborhood of the closure of V. Okay, and now we take U, distribution of compact support, such that U is smooth. So what do we want? We want now that Ku be smooth in V. Right. So we know that U is smooth in this neighborhood U. We want Ku to be smooth in a slightly smaller neighborhood V, such that both these neighborhoods contain a common point, but that's without loss of generality. So we want this to finish the proof. So to proceed, we can write this. We can write the following. We can write Ku as, right, using the linearity of K, we can write it as K of phi U plus K of 1 minus phi of U. Right, so this is just from the linearity of K. Right, we've written U as phi U minus phi U plus U. Okay, and so if we can show that each of these, we can show that both 1 and 2 are smooth on V. then we're done, right? Because K of U is just the sum of these two guys. So let's show that 1 is smooth on V, and, well, let's see, why is 1 smooth on V? Well, 5U is a test function, right? Because we have assumed that U is smooth on U, and phi is a test function. So this is C infinity C. Yeah, so this is just smooth, right? And what else? And K is separately regular. Again, this is a part of our hypothesis because we assume that K is very regular, and very regular implies separately regular. So these two facts together imply that K of phi U, or I guess I should say 1, right? K of phi U, in other words 1, is C infinity in all of omega, not only in V, but in all of omega, because separately regular operators map C infinity C to C infinity. So for number 2, we know that K of 1 minus phi of U is actually equal to, right, in physicist notation. So again, we're abusing notation very much here. And so we've shown this. We would like this to be C infinity. And notice, so every argument that I'll make right now, we can prove that it actually works in this case, but it's all very hand-wavy because, again, we're using physicist notation. So kind of assuming that this actually is an integral, notice that x is assumed to be in V. X is assumed to be in V, since we only care about smoothness in V. And y is assumed to be in the support of 1 minus phi. Because, well, that's the support of this factor here, this integral. Outside of the support, the integrand is 0, right? Quote-unquote integrand. So, and this is inside the complement of the closure of V. Right, so x and y are, they will never intersect, basically. X is in V, and y is in the complement of the closure of V. So they'll never intersect, and that means that this implies that xy is outside, or is off of the diagonal of omega times omega. And if xy is outside the diagonal, then remember we've assumed that K is very regular, so that means that K is C infinity everywhere we integrate over. Everywhere we're integrating over, K is C infinity. And so that means that we can just take the derivative over the integral side. We can just take like a d dx here, again, very hand-wavy, but that follows from the smoothness of every single factor in the integral. And so we can take as many derivatives as we want, and so that just proves that this left-hand side is C infinity with respect to x, at least in V, right, because we've assumed that x is in V. And so we're done with this lemma, right? So if K is very regular, then it is pseudolocal. And in fact, we can chain this up with another lemma, which is kind of a corollary of this lemma, that says if P is a linear partial differential operator on omega, and if K is K, again, from distributions of compact support to distributions, is very regular, then Kp, then if we can write, then, yeah, so then if we can write K composed of P equals the identity operator plus some R regularizing, then this implies that P is hypoelliptic So this is similar to what we had in our motivating example, right? We had some P composed with, we had some PD composed with I guess an E star, right? And that was equal to well, we didn't write it in terms of operators. We had PD on E equals delta times some smooth function W, or I guess little r, where this was C infinity, you know. So we have something very similar here, except written in terms of operators instead of distributions. And in this case, we will call K a parametrics. And what this is saying is that if our parametrics is very regular, then P is hypoelliptic. Okay, so let's prove this also. So just to recall a definition, so P is hypoelliptic if you have the singular supports of U contained in the singular supports of PU. So it's not that P doesn't make U any worse, but it's that P doesn't make U any better either, right? In terms of singularities. So this is what it means to be hypoelliptic. And again, in these kinds of proofs, usually we take the contrapositive, so we're trying to show that if PU is smooth in some neighborhood of x0, then U must also be smooth in a possibly smaller neighborhood of x0. So this is what we're going to try to show. And so since the type of proof is very similar to the lemma above, we'll just assume V and phi as above, as in the lemma above. And we know, so there's this familiar trick, right, of using the Leibniz rule and then pulling out the higher order term in Leibniz rule. So I won't reproduce the trick now. I think I've done it maybe in the last video. And we'll need it here to expand to note that P of phi U is equal to 5 PU plus this W, where W is a distribution of compact support and W is 0 on V. So these two facts will be important. And we got this with the Leibniz rule, and we've pulled so this is the term where alpha equals beta in the sum. So we take the Leibniz rule, and this is the term alpha equals beta. We pulled that out of the sum, and what's left in the sum is this W with these two important properties. So this will be important, and then we will note that on V, on the neighborhood of V, we have U equals the identity operator on U, which equals the identity operator on phi of U, right, because we're inside V and phi equals 1 in V. And this is equal to, by definition, right, of since K is a parametrics, Kp of phi U minus R phi U. Okay, and now notice we have P of phi U here, and we know that P of phi U is equal to this up here. So then we can just substitute this in and use the linearity of K to obtain this equals K of phi PU plus KW minus R phi U. So we'll call this 1, we'll call this 2, and we will call this 3. Again, same as above, we now want to show that 1, 2, and 3 are C infinity on V. Right, I want to show that all three of these guys are C infinity on V, and we are assuming that PU, assume that PU is C infinity on U. Okay. So how do we proceed here? Let's start with 1. So 1 is, so we first note that K is very regular by assumption. So K is very regular, which means it is separately regular. And this is the same way we've proved. Same argument as above here, right? K is separately regular, and this phi u c infinity c. In this case, it's phi of pu, right? We have pu is c infinity on u, and then phi is a test function, so phi of pu is c infinity c. So K very regular. K separately regular actually implies what we want. Because K maps c infinity c to c infinity. Okay, so number 2. For number 2, we will use that W is 0 in V. And since W is 0 in V, oh yes, K, okay, so K is very, very regular by assumption, right? And what we've proved in this lemma is that very regular implies pseudolocal. So pseudolocality implies that if something is smooth on a region, then it will remain smooth after application of V. So W is 0 on V, which means it's smooth on V. So since K is very regular, this implies what we want, which is that K of W remains smooth on V. And lastly, we will, the last one is obviously C infinity because R is regularizing. So here in this proof, it's very nice because there are 3 reasons. So each one of these is smooth for a reason, and we've used all of the definitions of regularity that we know. We've used separately regular, we've used very regular, and we've used regularizing. So we have now proved that if we have a very regular parametrics to P, then P is hypoelliptic, right? So our parametrics can be a pseudodifferential operator, right? It does not have to be a differential operator. So this result really highlights the use of this theory. Right. Okay. So, well, actually, not only this result highlights the use of the theory, but we've already seen how useful pseudodifferential operators are when we characterize the regularizing operators using them, right? So I think this is all I had to say on the, oh no, sorry, we still have not shown that pseudodifferential operators are pseudolocal. So theorem. Pseudodifferential operators are pseudolocal. And the way we'll show that they're pseudolocal is we will represent a pseudodifferential operator as a Schwartz, as it is an operator defined by Schwartz kernels, and we'll show that the kernel is very regular. And since we know that very regular operators are pseudolocal, then we will have finished. Okay. Not only that, this proof will imply that since we have this lemma here, we'll show which says that a very regular parametrics implies that P is hypoelliptic. Since we will show that pseudodifferential operators are all very regular, that means if we find a parametrics that is a pseudodifferential operator, that means a pseudodifferential operator parametrics, this implies that that P is hypoelliptic. Right. Okay. So pseudodifferential operators are pseudolocal. Let's start. So what we wanted to do, right? We wanted to show that they are very regular. So we know that pseudodifferential operators are separately regular. We've seen that above. So all we have to do, so we know they're separately regular. So it is enough to show that the associated kernel A of xy is C infinity off of the diagonal. And this is equivalent to saying that gx times A of xy times h of y is C infinity. Not only outside of the diagonal, but everywhere. So what, so this is for every gh C infinity C with disjoint supports. So the disjoint supports are important because, let's just first give an intuition on what's going on here. So we have omega times omega, omega times omega, and this is the diagonal, right? We do not want A to be smooth. We want A to be smooth outside of this diagonal, right? So what we're doing here is we're multiplying A by C infinity C functions that have disjoint supports. So meaning we have G, we have the support of G, let's say here, right? So this is the support of G, and the support of H might be here, right? So then we have G of X times H of X has support here, right? So we're essentially multiplying something that has support here in this little square with our Schwartz kernel A of xy, which then gives us something that has support obviously outside of the diagonal. So we're just measuring, essentially what we're doing is we're measuring A on these little squares that don't intersect the diagonal, right? So this is support of G, and this is support of H. And so this is very interesting, right? It reduces the problem of finding that a property holds outside of the diagonal to showing that a property holds when you have two functions with disjoint supports. And that's essentially what this outside of the diagonal stuff encodes, right? It just encodes that two sets don't intersect each other. Okay, so let's get started then. So suppose A of x, y, psi is an S of m. So this is an amplitude. Is an amplitude it's an amplitude of the pseudodifferential operator A. So I'm just going to do this again very quickly and hand wavy. So given for any u in C infinity of omega, we have the gx of A hu x. So again, this is just this. So this equals, by definition, this equals this equals this. Where this A sharp is equal to G of x times A x y xi H of y. And you can check this that this actually holds, right? This is just the application of the definition of pseudodifferential operator. And okay, so now we just start manipulating this expression. So this is equal to, we can take, so I'll just stop writing this to, I'll continue writing it actually. So we have 2 pi to the minus n double integral, and now we can just multiply and divide by x minus y to the 2k. We'll have this e here, a sharp, and dot dot dot. So what we've done is we've multiplied and we've divided here. Now we can notice that, so we can use now this e here, we can use this convenient e here to transform this multiplication in the spatial variables to differentiation in the frequency variables. So this x minus y here by the chain rule becomes this Laplacian with respect to xi to the k. And on this right side we have everything remains the same. And now finally using the product rule, or sorry, integration by parts, same thing. Using integration by parts, we can now transfer these orders of derivation to another term in the integrand. Right, and we use integration by parts 2k times to get e, and we've transferred this Laplacian to this other side. Right, and so now notice that we have now our symbol differentiated by a differential operator with respect to xi of order 2k, right? 2k because this lambda, or sorry, this delta has order 2, and so this is raised to the k. So this is the differential operator of order 2k. And notice that this a sharp has the same degree, or the same order as the symbol a, which is order m. Right? We've assumed that our pseudo-differential operator, assume that a is in psi m, and so a and a sharp are both symbols of order m, or amplitudes of degree m, whichever you prefer. And so by throwing this guy onto the left-hand side, what we've essentially done to the estimates is we've put an extra 2k on the right-hand side of the estimate. So let me just write this out a little bit more clearly. We have the estimate that defines pseudo-differential operators, which is, let's say, d alpha xi d beta x d gamma y of a sharp less than or equal to some c times 1 plus xi to the m minus alpha. And so this is a order m, right? So we have an m here, but the same operator which had symbol a sharp now has symbol equal to all this. We can essentially, for the purposes of the estimate, we can ignore this part with x minus y, since the estimate only really cares about the decay with respect to xi. And so we have the derivative with respect to xi of order 2k. So what we've done here is we've essentially added a derivative here, right, with respect to xi of order like 2k, right, 2k here. And what this does so we can just absorb this into the this alpha here, so this is going to be like plus 2k. Just imagine this notation means what you think it means. And so on this right-hand side, we'll have alpha plus 2k. Right, we have this minus here, so this will distribute minus 2k, and we'll rewrite this as 2k minus alpha. So notice that we have a new order here, right? So this is so that means a sharp. So gx g. I'll just write g. GAH is the operator induced by a sharp, which has order m. But this is also the operator induced by all this, which has order m minus 2k, right? So So A, let's see, yeah. So A is in psi of m minus 2k. But this k was arbitrary, right? This k was arbitrary because we've introduced it here by just multiplying and dividing by x minus y to the 2k. So we can take it as large as we want, and so this implies that A is in psi of minus infinity. So it in fact is a pseudodifferential operator of order minus infinity as we wanted. So a very interesting proof. So we're done with the proof, and just a comment. All we wanted to show in this proof is that this guy, this Schwartz kernel here, is C infinity. That's all we wanted to show in the proof. So we wanted to show that a distribution is C infinity. What we did to get there was first we wrote this distribution as the Schwartz kernel of an operator. So first we wrote the distribution as the Schwartz kernel of an operator. Then we expressed this operator as a pseudodifferential operator. Then we manipulated the symbols a little bit to show that the differential operator is in fact, the pseudodifferential operator is of order minus infinity. And then we used that pseudodifferential operator. We used essentially the first theorem that we proved, which is the characterization of regularizing operators, which is that pseudodifferential operators of order minus infinity correspond to Schwartz kernels that are smooth. So that means the Schwartz kernel of this operator is smooth, but we know the Schwartz kernel of this operator, which is this. And so we're done. Right, so this is a very roundabout way of showing that a function is smooth. I thought it was pretty funny. Okay. So the last thing I wanted to prove was that pseudodifferential operators, not only are they pseudolocal, but they exhibit a sort of refined pseudolocality. So refined pseudolocality. And for that, I'll need a few definitions. So one definition is of a pseudodifferential operator being properly supported. So a pseudodifferential operator is properly supported if both A and the transpose of A map the distributions of compact support to the distributions of compact support. So in lieu of the property of being local, this is the second best thing, right? We're not saying that a pseudodifferential operator, if it maps something that has support here to something that has support here, or possibly smaller, we're saying that a pseudodifferential operator maps something that has support here to something that has still compact support, right? At least it doesn't explode the support. So that's what we're saying. Neither the pseudodifferential operator or the transpose explodes the support. Okay, so another definition that we'll use is the definition of microsupport. So we say that a pseudodifferential operator A is regularizing on a neighborhood of some point x0, xi0 in omega times Rn excluding 0 if there exists a function g and a cone gamma 0 such that the symbol, or the symbol representative more rigorously, A of x psi of A has the property that for every alpha and beta multi-indices, there exists a constant depending on alpha, beta, and m actually, such that the supremum over omega of the derivative of alpha, derivative of x, derivative of xi of gx alpha x xi is less than or equal to c times 1 plus psi to the minus m for every xi in gamma 0 and for every m greater than or equal to 0. So to finish the definition, the complement in omega times Rn without 0 of where A is regularizing is the microsupport of A. So is the microsupport of A. So this is very similar to the definition of the wavefront set of a distribution. Right, we're saying that we have this set in the cotangent bundle where we essentially have rapid decay. We have rapid decay of the symbol of the pseudodifferential operator, right? In the case of distributions, we had rapid decay of the Fourier transform. Here we have rapid decay of the localized symbol. We also have, with respect to these derivations. And so this rapid decay of the symbol implies that A is regularizing in a direction, and the directions where A is not regularizing are the directions inside the microsupport. So this is the notion of the microsupport. And we have two lemmas to help refine your intuition on microsupports and their interaction with wavefront sets. So the first lemma, I'm always putting one m on the lemma, right? So with two m's. So we have U. So if U is a distribution, and x0, xi0 is a point on the cotangent bundle, then the following are equivalent. One is that this point is not in the wavefront set of U. The second is that there exists gamma, an open conic neighborhood, of x0, xi0. Such that if A is I'll just do PS, properly supported. So if A is properly supported in omega with the microsupport of A fully contained in this gamma, then AU is a smooth function. So what this is saying, so let's see if I got this right. So there exists an open conic neighborhood such that if A is properly supported in omega support here, then we have this. Okay, so what this is saying is that if we have, so this is the cotangent space for a fixed point. This holds for all points. If we have, let's say, the wavefront set of U here, and if we have the microsupports of A here, notice that they do not intersect at this point, then this implies that AU is C infinity. AU is C infinity. That's basically it. That's basically what this thing says. It's that if we have a point not in the wavefront set of U, so let's say a point here, then there exists an open conic neighborhood around that point, such that if the microsupport, let's say an open conic neighborhood around the point here, such that if you have the microsupport in that conic neighborhood, so here's the microsupport, then A of U is in C infinity. Okay. Right. So what else? Oh, we have, I guess, a more qualitative version of this lemma. More qualitative version is that you could say that, again, so assume that we have a pseudodifferential operator that's properly supported in omega, and U is a distribution. So then, no, just assume we have a properly supported pseudodifferential operator. Then A, do we need to be properly supported? We might not need it to be properly supported here, but yeah, let's just remove this properly supported. If A is a pseudodifferential operator, and it's regularizing, if it's regularizing on gamma, then this is the same thing as saying that A of U is C infinity on gamma for every distribution U. Right, so this is essentially saying that if we have a place here where A is regularizing, then A of U, independent of the singularities of U, A of U will always be C infinity in this region. Okay. So now we can enunciate this final theorem, refined pseudolocality, which is that if we have a pseudodifferential operator that's properly supported in omega, and U is a distribution, then the wavefront set of AU is contained in the wavefront set of U intersection with the microsupport of A. And so to prove this, all we need to do is to show that this wavefront set of AU is contained in this, and the wavefront set of AU is contained in this, right? So we just need to show those two things. That this wavefront set of AU is contained in the microsupport just directly follows from the qualitative lemma, right? So it just follows from this, because, so suppose we wanted to show the converse, right? Suppose we wanted to show that, say, the regular set of AU contains, so instead of the microsupport, it's the regularizing set of A. So we want to show this. And in fact, this is the case simply because of the qualitative lemma, right? If we have a point in the regularizing set of A, right? Regularizing on gamma. Let's say A is regularizing on gamma, right? So we want to show that gamma is also in the regularizing set of AU. And in fact, it is, because AU is C infinity on gamma. So we've shown this part, and now all that's left to do is to show this part here, which is that the wavefront set of AU is contained in the wavefront set of U. And to show this part, all we have to do is, so again, we want to show the converse, so we want to show that the regularizing set of U is contained in the regularizing set of AU. Okay, so suppose we have some open cone gamma in the regularizing set of U. We want to show that there's possibly a slightly smaller cone in the regularizing set of AU, right? Or actually, ideally, we want to show that gamma is in the regularizing set of AU. So let gamma prime be another cone, another open cone, and we want its closure to be contained in gamma. And we also want the closure of gamma prime to be conically compact, which just means that the projection onto omega is compact. Right? So its projection onto the base space is compact. Okay, and so now we can write. So it's an easy exercise to show that you can write A, which is your pseudodifferential operator, as A prime plus B, where gamma prime is contained in the regularizing set of A prime, and the complement of gamma is contained in the regularizing set of B. Right? And so to illustrate what this is saying, we essentially have for every point in the base space, we have this going on in the cotangent space. So this, let's assume that this is the complement of gamma, and this is gamma prime. We have that B is at least regularizing here, and that A prime is at least regularizing here. Right? At least. It could be regularizing in more places. Okay, so note that it's now enough to show. So we want to show that gamma is in the regularizing set of AU. This is what we want to show. And this is, so to show that gamma is in the regularizing set of AU, this is the same thing as saying that the wavefront set of AU does not intersect gamma. Right, the wavefront set of U does not intersect gamma. And to show this, all we have to do is to show 1 and 2, where 1 is that the wavefront set of A prime U does not intersect gamma prime, and 2, which is that the wavefront set of BU does not intersect gamma prime. Does not intersect gamma prime. And then we just let gamma prime go to gamma, and that's why this proves this, right? Because A is just A prime plus B, and then we have this statement here and this statement here, and so if we take gamma prime to gamma, we have this, right? So we just have to show these two here, 1 and 2, and 1 1 follows again from our qualitative lemma, right? So 1 follows because, let's see, why does the wavefront set of A prime U not intersect gamma prime? Well, A prime is regularizing here, right? So let's just start writing green. A prime is regularizing here, in gamma prime at least. And where A is regularizing, according to our qualitative lemma, AU is C infinity, is smooth. So A prime U cannot be so A prime U must be smooth at least in here, right? and the wavefront set is the places where A prime U is not smooth, and so it can't intersect gamma prime. So this check, we have this, right? For this other one, we have to use two facts. We have to use that that gamma is not in the wavefront set. That actually gamma does not intersect the wavefront set of U. Right, we have to use that gamma does not intersect the wavefront set of U, right? Because gamma is in the regularizing set of U. So gamma is in the regularizing set of U. So gamma is everything out here, right? This is gamma. Because this is gamma prime, complement of gamma. So everything outside is gamma. And so this is contained in the regularizing set of U, right? So the regularizing set of U could be even larger than this. It could be, for example, this. So maybe this is the regularizing set of U. But remember, B is regularizing in here. So B is regularizing in here. And outside of here, we have that U is C infinity. So that means the union of where B is regularizing and where U is regular is the entire cotangent space. And then using that, using lemma 1, or this lemma here, that shows that that AU is in fact C infinity. And sorry, the AU is where would AU be? C infinity? Sorry, I had to take a break here. So what was I? So I was proving number 2, and so actually we have that from number 2. So number 2 just follows from this lemma here, right? The quantitative lemma. We will have that BU. Not only does the wavefront set not intersect gamma 0, the wavefront set doesn't intersect anything because BU is C infinity in all of omega. This is C, so BU is actually C infinity because of part 2 here. Because of part 2. So we have that x0 xi 0 is not in the wavefront set of U for every x0 psi 0 in gamma, right? Because of this, for every x0 psi 0 in gamma. So then there will be a cone in the neighborhood of x0 psi 0, meaning that there will be an open cone that will at least be equal to gamma, because this holds for every x0 psi 0 in gamma, such that if A, in this case B, right, in our case B, has microsupport in this gamma, then AU is C infinity, or in this case BU is C infinity. So where is the microsupport of B? Well, the microsupport of B is somewhere outside of here. Remember, this is gamma. So yeah, in fact, we do have the microsupport in this gamma. We do have the microsupport of B inside this gamma. Sorry for completely messing up this drawing, but we have gamma out here, and the microsupport of B is in fact in here because B is regularizing in here. And so we have that BU is C infinity, right? So again, sorry for messing up the drawing, but this finishes our proof. So we've just proved this refined notion of pseudolocality, which says that we have pseudolocality with intersection. We can make it better depending on the microsupport, right? The smaller the microsupport of A, the better this estimate on the right-hand side gets. Right. Okay, so that's all I had to say for today.